This screencast is coming for you from my chemistry lab. Hopefully there won't be any interruptions while I'm doing this. We're going to be talking about work and energy, two words that are very, very closely related. As you might imagine, on an everyday basis, whenever we do work, we exert energy. And so energy and work in physics, we're going to see, are interconvertible, which means you can go back and forth. Therefore, they would each have the same unit of measurement, the joule of energy, the joule of work. We're going to be connecting these two throughout the chapter and coming up with a whole different way to solve complex problems. Now, energy, of course, is one of the most important concepts in science. We talk about energy in every single branch of science that you can imagine. And it's one of those terms that we kind of think we know what it means, but we really don't know what it is. There is no actual substance or material or particle that represents energy. We talk about energy all the time. We don't necessarily know what energy is. It's something that we take on faith. And please keep in mind there are two kinds of faith. There is the idea of a blind faith, for which there is very little basis or foundation. And then there is informed faith that is based upon evidence. A lot of people talk about why should they have faith in God or faith in the Bible, and they think that that means blind faith, or they assume that all faith is blind, and that is totally false. We have very, very good reason, from a scientific point of view even, to believe that there is a God based upon evidence. And the evidence that we see throughout creation in terms of its magnificence, its glory, its intricacy, its design, its fine-tuning, this gives us the idea that the inference to the best explanation for why the universe is the way that it is because there is a creator God, and that the universe is going to reflect the creator in this way. We would expect that, given the character of God and given what we discover about the universe. That would be an informed faith based upon evidence. And here, of course, we're talking about this is the inference to the best explanation. It's a better explanation than if the universe and its design and its order and its fine-tuning was just the result of accident or chance. Of course, also, there is no explanation for where the universe came from in the first place. And that also would infer that there is a creator because there is a creation. And this creation has energy in it. We take that on faith that there is such a thing. And we have lots of evidence, such as the explanatory power of energy, as you're going to see throughout this chapter. So every person has faith in something. The question is whether that is a blind faith or is it an informed faith that has evidentiary foundation. So moving right along, when we talk about energy, energy comes in lots of different forms, and the very fact that we can do mathematics about it and convert it from one form like mechanical or chemical or electromagnetic or nuclear into another form supports our faith that there is such a thing as energy. And the mathematics enables us to make these conversions from one form to another. And we even can begin to conclude that energy is neither created nor destroyed. It just changes form. We can even say that mass is one form of energy. And later in the book, we'll get to Einstein's famous equation that you can convert mass into energy and back again. In fact, nature does this naturally also. So the idea of energy going from one form to another and the fact that the total energy of the universe is always constant. It just changes form and ultimately ends up as a form of low temperature heat. All of these essential concepts give us reason to believe that there is such a thing as energy. And so when we take this on faith, this is a very informed faith based upon all the reasons that I have mentioned. Now, energy and work are very related. It takes energy to do work. And when we do work, we need to recognize that there are different definitions of work. Just like with energy, there are the everyday, ordinary uses of the word, and then there are the very carefully defined definitions of energy and work that we use in physics. If you don't carefully define something, you're not going to be able to use mathematics with it. So we can say, I got to do work, I got to go to work in the morning or go to the job site and do work and get paid for that. We have the everyday definitions, your chores. You might have chores to do at home, like mowing the lawn or washing the dishes. And in physics, when we talk about work, we're talking about exerting energy by means of applying a force through a certain distance. In other words, if I am standing still but holding a very, very heavy weight, let's say some barbells or a couple of loaded suitcases or a bag of concrete on my shoulder, but I am not moving left to right, by the physics definition, I am not doing any work. Work is defined as force times distance, as long as the force and the distance are moving in the same direction. Now, if I take that bag of concrete and I lift it from the ground up to my shoulders, then I am doing work in this direction. Then when I walk from left to right to take that bag of concrete to the job site, then I am doing work in this direction. But there has to be some displacement, d. And it might be in the y direction, and it might be in the x direction. There has to be some type of displacement when we're defining work as the way physicists do it. So if we're moving from left to right, the work that I'm doing is the force that I'm exerting in the x direction times my x displacement. And the unit of work is called the joule, and a joule is a Newton meter, and that means my force times my displacement, or we could use the letter d, or in the y direction we could use the letter y. And so a joule is a Newton meter, but you should know that a Newton, if you think of this definition, force equals mass times acceleration. Mass is in kilograms, acceleration is in meters per second squared. So a Newton is a kilogram meter per second squared times a meter, which gives me these as my fundamental units of work. A kilogram meter squared per second squared, and that is what a joule is. And it doesn't matter if we're talking about work or energy. We could look at the formula for potential energy and kinetic energy, as we'll do a little bit later, and we're going to get these same fundamental units. Right? Let's see, right here I mean kilogram meter squared per second squared. Work is a scalar quantity. We don't, the displacement is, and the force are vectors. So that's where the direction comes into play. There is the old-fashioned U.S. customary unit of a foot-pound as opposed to a Newton meter, and we will probably not use the foot-pound at all in AP Physics. Now, sometimes the force that we're exerting is not in the same direction as the distance. Imagine that we have a box resting on a plane surface, and we are exerting an applied force, F sub A, and it's at some angle theta. Well, in this case, what we need is my horizontal component of the applied force. And that horizontal component would be FA cosine theta. And that's where we get this from, right here. So if my force is not acting exactly in the same direction as the displacement d, that's where the cosine theta comes in. So again, work always requires a system of more than just one object, because something has to be exerting a force on that object. And work can either be positive or negative. It depends on the direction of the force. You can be doing work on something to move it in the direction of some displacement, but you also can be doing work in order to overcome friction, which is acting in the opposite direction. So you can have positive or negative work that's being done, and you need to designate up front which is the positive direction and which is the negative direction. Again, if we think of an object and we're exerting a force in this direction, that's my applied force. We can have a force of friction in the opposite direction. And that, of course, implies that there is a mu. And so if we are moving it towards the right, my applied force is going to be greater than my force of friction. Or if we're moving at a constant speed, then my applied force, assuming it's parallel to the surface, equals the force of friction. But the force of friction is, we're doing work against that force of friction, and the applied force is going in the opposite direction. We can also have varying forces. And you can see in this treatment, in this chapter, regardless of whether the force varies or not, we are interested in the total force that is being done from start to the end. What happens in the middle of the start and the finish time, it seems to be irrelevant, which is going to be kind of nice when it comes to solving these problems. Now, by the way, whenever you see these quick quizzes down here, I would suggest that you test yourself to see how well you understand the concept, and then you can look these answers up in the back of the book. It's a way to test yourself. You could pause your screencast right now and test yourself. Give yourself a little quiz. Now let's take a look at this problem here. Now, there are a lot of math problems that are done on ice or on snow for some reason. And of course, that's either to have no friction or eventually to have a problem that will have friction, like in this one. So here we have a man hauling a whole bunch of salmon. And of course, no animals were hurt in the performing of this physics problem. All of these salmon were gathered at the moment that they happened to die painlessly. So, and the individual here then is going to capture these salmon. They are now frozen and safe to eat, and he is going, or she is going to feed the family with the salmon. And so we have an applied force right here. That's my F sub A. And we have our force of friction acting, opposing the motion. We have our force of weight acting down, mg, force of weight, or you could say the force due to gravity. You should be used to all of these terms. And then we have our normal force acting up. So in this particular problem, find the work done when the force is horizontal. If the force was just going horizontally and not acting at an angle, there would be no cosine theta, and the total work would be my force in the x direction times my displacement in the x direction, and we would get 600 joules. Now, if we have the applied force acting at an angle of theta degrees, then my applied force is going to be F cosine theta. There's my applied force. F, we want the horizontal component of that. And here's my displacement, which doesn't change. And now you'll notice that my answer is less than 600 joules because I now have the F cosine theta as my force. And so you get less of a force acting on your sled filled with salmon or your box or whatever it is you're moving, the greater your angle theta. Ideally, you would try to pull as close to theta equaling 0 as possible to maximize the amount of work that's going to be moving the object that you're pulling. Now, vocabulary word, the word dissipative. A dissipative force is a force in which the energy gets dissipated, which means it's not all available in order to accomplish the work that you want to accomplish. And that is usually the result of friction. Friction, of course, is when some of the work you're doing has to overcome the resistance to that work that you're trying to accomplish. And that means you're going to be overcoming friction, and that ends up as heat. And then, of course, the heat then gets absorbed by the system. It gets lost to the surroundings, and eventually it contributes to the overall heat of the universe, low temperature heat of the universe. And so in a sense, you could say every time we do work, we contribute to global warming, and not just global warming, but universal warming, which contributes to its spreading out and gets spread out over the entire universe. That's something we're not going to worry about until we get to our chapter on thermodynamics later in the semester. So sometimes friction is good, sometimes friction is not so good. It just depends upon the kind of friction. So the frictional force is generally dissipative. You lose some of the energy due to heat. Now, even surfaces that appear to be extraordinarily smooth have some microscopic interactions going on between the molecules that make up, in this case, the bottom of the razor and the molecules that make up the surface that razor is going along. It might even be the surface of your skin someday, guys, when you shave. Anyway, my point, and I'm trying to poke fun at the guys if they haven't started shaving yet. Anyway, the idea here is even at the microscopic level, you can see that this surface is very irregular. And there's going to be an uneven, at the microscopic level, uneven rubbing of the surface of the razor over whatever the surface happens to be. Also, even if we were able to make this smoother and smoother somehow, or coat it with a surface, you are still going to have some energy lost due to friction because of the fact that you have what are called intramolecular forces. These intramolecular forces, sometimes called dipole or dipole non-dipole intermolecular forces, and even London forces. You might remember all of those names from chemistry class. These intramolecular forces would be the forces of attraction between the molecules of one substance and the molecules of another substance, not to be confused with the intermolecular forces, the natural dipoles, or even the ionic bond attractions. So there's always going to be these frictional forces, even at the molecular level, that's going to cause a dissipation of energy and the production of low temperature heat. Now, let's continue with this problem here. Let me make sure I didn't skip anything. Okay, good. There we go. Calculate the work done by friction, reading right here, when an object is acted on by an applied force. So now we're going to go back to that example 5.1, and now we're going to have a coefficient of kinetic friction, and there it is, which immediately means that you've got this equation right here. mu equals the force of friction divided by the normal force. So when we solve this equation for the force of friction, we get mu times the normal force. And because we're on a horizontal surface, my normal force equals my force of weight, assuming my applied force is horizontal. This would be the normal force and the force of weight. And so therefore my Fn can be equal to Fw, and Fw is the mass times gravity. And so when we apply our condition of equilibrium in the vertical direction, the summation of the forces in the y direction equals 0. In other words, my up force, the normal force, equals the down force, the force of weight. We find that my frictional force, the work that's going to be required in order to overcome friction, means that I have to take my force of friction, and it's negative because it's opposing the motion that I want. My force of friction would be, whoops, this way. This would be my applied force. So my force of friction acting in the negative direction, not the positive direction, times the distance x, my force of friction equals mu times the normal force, which is what I said here. And then the normal force is also the force of weight, which is mg, and that's where we get this term right here in this equation. So now when I plug in my numbers, I get 490 joules acting in this direction. I should say the force is acting in that direction, the force of friction, and that's how much energy it requires in order to overcome the frictional forces. And so my net force is going to be the original 600 joules of energy minus the force of friction, giving me a net force going towards the right that will be the work being done to move the object to the right. All right, now let's continue on and wrap things up with this problem right here. So if this is my object resting on a surface, notice my vector diagrams. I've got the normal force acting up, the force of weight acting down, the force of friction. But now my applied force is acting at an angle of 30 degrees. So I resolve my applied force, as always, when it's not acting in the x or y direction, into its y component, which is Fa sine theta, and its x component, which is applied force cosine theta. And once again, I can do my up forces equal my down forces. And so if the summation of my forces in the y direction equals 0, what we're going to have are my up forces, which is the normal force, plus my component, which is Fa sine theta. Those are the forces acting up, and those equal the force acting down, which is Fw. And then we can also say that my right forces either equal my left forces, or if it's accelerating to the right, my right force, which is going to be Fa cosine theta, minus the force of friction, which is the left force, equals ma, where A would be the accelerating force. That's how we treated this back in chapter 4. But now in this way that we're going to treat it as far as energy is concerned, once I've calculated that the work being done in order to overcome friction is going to be my force of friction times my distance, delta x, and the force of friction is going to be mu times the normal force, which we showed you just a few minutes ago, and my normal force, which I solve for you right here, the summation of the forces in the y direction equals 0. My normal force then is going to be my Fw minus Fa cosine sine theta. When I solve my up forces equal my down forces for F sub n, I get Fw minus Fa sine theta, and that's what we have right here. And now we plug our numbers in, and so now we can solve for the work being done to overcome friction, which is 430 joules. So therefore, my original amount of work from the earlier part of the problem, 51b, 520 joules, minus the work to overcome friction, 430 joules, gives me the remaining work, 90 joules, that's available to move the object toward the right through distance x. And we're going to stop right there.